Okay, welcome to another session of EL 164 online. Today we're going to talk about counters, another important feature of PLCs. Okay, I'm going to pull up the laser pointer here and let's go ahead and get started. Okay, so the first piece of this that we're going to talk about is, again, like the timers, the chapter 7 with the timers, this is chapter 8, where they get into rather in-depth using the counters in a SLC 500 or a RS Logix 500 format. We're actually using the Control Logix 5000, so that is a little different format. So we're going to kind of briefly discuss some of these formats. They're very closely related in the sense that the addressing works pretty close. Only difference is that we're not forced to use a C5 or any of that nature. We can call them counters or Joe's counters or Fred's counters, whoever counter we want to call them. But in this particular case, they happen to show us the C5:3, which is again the 500 version of the counter. So noting that just like the timers, there are 3 words associated to them. There's even in the 5000, it'll still be 3 words. The difference is that each one of these words is going to be 32 bits long, not 16 bits long. The individual bits or the control word bits will be the same. The counter up, counter down, done bit, over, under, and I can't remember what UA is. We'll be getting that in a minute here. The preset value is going to be a 32-bit word instead of 16, and the accumulated value will be a 32-bit word instead of 16. So counter instructions. So basically, a counter, essentially, as you can guess, it's pretty intuitive. It's used to count. Some of the aspects in industry, things that you will be seeing in industry, something like this. We use something like this little device here on our dies, where a die is something you put inside of a press, and every time that press closes, it pushes this die together, and this die puts dents and holes in metal that gives you the final product on the output of it. Well, you need to know from a tool wear perspective how many hits have been hit on that die, and this type of counter works really well for that. So every time that die closes, it would increment that count by 1. And when you went in, when the die went into the tool room to get its regular maintenance done on it, the tool room guy would put the new sharpened tools in it, and then hit this reset button, bringing it back to 0. So the next time that die went back into the press, it would be reset to 0, so they'd know exactly how many hits they got out of it before it needed repair. This is a very common practice, and it works the same way as a digital or a counter in the PLC world works. It looks for a trigger and has a reset to it. So we'll be digging into that here real soon. Here's some digital counters, things that you may or may not run into in industry. Some of these components you'll see in like a DIN rail mount type connection, or even someone through a cut hole in a control panel. It'll be actually sitting. You'll be able to see the display. You can set these up so that when they reach a certain count, it closes the contact. So you can use different outputs or whatnot you wanted to use for it. Maybe even something like this, maybe have like an Ethernet cord that plugs into it that translates that information to some other device that lets it know that what count it's at and how close it is to the end, that kind of stuff. All these components here are about the same cost as a micro PLC nowadays. So something that you may not even consider, but if you put a little PLC in that application, you could achieve the same process. Here's an application where we're actually just using a sensor to read product as it's going by. And as you can see here, they're just keeping track of the counts. Here is actually an older version of the ladder diagram. They're kind of illustrating here. I'm not really getting all the details, but there was a time when like PLC 1 and PLC 2 where the counter actually looked something more like this, and which is kind of outdated now. So you can see a counter up, counter down, but now you're going to see something more along the lines of these guys here, something more of a box type thing. That's I'm going to try to get us there. Here they're kind of illustrating how a counter up can increment and a counter down decrements. So every time it sees a count on this input, it counts up. Every time it sees a count on this input, it counts down. And so you can use two different counter types with the same address to count up and count down. So I'm going to start with the up counter. This is the up counter. This looks very similar in both the 5,000 and 500. There's no real variance here. I remember on the timer there was the base. The one had a millisecond base, and the other one had a choice of bases. The counters are pretty much identical. There's nothing really different here. So you have the address, the counter address, the counter preset, and the counter accumulated values. So here's kind of what you're going to see in a PLC program with a counter. You're going to see some sort of signal in front of it. This is going to be the component that's going to be counted. So every time this contact closes, this accumulated value will increment by 1. When this accumulated value reaches the preset value, the done bit turns on. Every time this contact closes, the CU will turn on as well. Here's a timing diagram. As you can see here, every time that this goes from a false to a true statement, this is the input to that sensor, to that block, you will see this thing increment by 1. It holds that information until what? Till we hit the reset value. We hit that reset, and at that very point, it drops it back to 0. And here's an example of how that actually works. Noting that every time they press the 1, 0, that increments by 1, and the counter turns on, the CU turns on. It hits 7, and the done bit turns on at that very moment. When you come down here and hit that reset value, that value goes back to 0. Noting that C5:1, that address has to match this address in order to reset. Very cool. Okay, so we're going to break down these a little bit better. So here, as we noted before, we've got basically here they're showing us 16 bits, excuse me. In our current configuration, we will be having 32 with the 5000 series software, but for example purposes, this is good enough here. So as you can see here, we're looking at accumulated word, a preset word, and then individual bits of each one of these components. That's how the table pretty much lays out for both. So we have the counter up enable, CU enable bit. It's true whenever the counter instruction is true. The count down is true whenever the count down counter instruction is true. So this CU is associated only with the counter up. The CD is only associated with the counter down. It makes them both available for whether you have a counter up or counter down, so that way they could use one common control word for all the counters. That's their design behind that. So keep things simple. We like things simple. The done bit is true whenever the cumulative value is equal to or greater than the preset value. So that means that quite often what you'll see is the done bit come on, so you're counting, and you hit where the accumulated value reaches the equivalent to the preset value, and the done bit turns on. But if you keep triggering that input, so the counter keeps counting up, that done bit stays on. It doesn't turn off after you've passed that after you've hit the preset value. So here's a couple of ones that you don't use a whole lot of, but you need to be aware of is the overflow bit. That's true whenever the counter counts past its maximum value. Now remember, this 32767 is the maximum numeric value you can put into a 16-bit register. When we get into the 32-bit register later in this segment, you will see it's a much larger number, so we can count way higher. Okay, next piece is the underflow bit. It's true whenever the counter counts below a negative 32768. So that is the lowest number we can get to. Once we get past that point, then the negative or the underflow bit turns on, the UN. So then here's the accumulator bit. So the UA bit, updated accumulator, is used in conjunction with an external high-speed counter. So when we have a high-speed counter card or something of that nature, we're using that. The preset value, I've not really used that in the past, so I don't have a whole lot of background with it. The preset value word, pre specifies the value that the counter must count to before it changes the state of the done bit. So again, this is the value that you enter into the counter to say when you reach the value of what number you've ever picked out. When it reaches that value, then the output turns on. And of course, the cumulative value is the current count. So here we are, we're looking at the CU, or the counter enable, or the counter, it'd be CD for counter up enable, counter down enable. The DN is a done bit, of course. This is probably the most common bit used for a counter. The OV for overflow status, I never use that much, but it gives you the idea that you're over the value of the counter. And then the C5:50 here, reset. This is how we're resetting this counter back to 0. We can reset this to 0 at any given time. It doesn't have to be at the done bit. It can be reset anytime. So like in this particular case, if preset set to 10, when we're at the cumulative value of 5, we could hit the reset and it would reset it back to 0 at that point. Okay, here's where we're going to find the counters. Like we found the timers under timer counter file folder. We've got the timer on, timer off, retentive timer. We've got the counter up, counter down, and the reset. So here we are where we're dealing with the counter up, counter down, and the reset. So again, just count up, count down. And high-speed counter, never use that in the PLC, so I don't have a lot of background to talk about that. So I'm going to stick with just the counters here. So here we're looking at an application, our infamous motor start-stop circuit. So here we got the stop signal here, the start signal, some sort of done bit and this counter, and then the motor seal-in circuit. Should look really familiar to everybody by now. So we hit noticing that the stop is a normally closed, so it's open here. The start button's normally open, so that's an open signal here. And then the reset here, down here, is normally open as well. So when we hit the start button, the motor's going to click on here, that's going to come on, and that's going to click this on, and it's going to count this by 1. So then next time we hit the stop button, it's going to turn this off, and we hit the start button again, it's going to start it. And so basically you have to turn this motor on and off a total of 10 times before we get to the done bit. When we hit the reset, then excuse me, I should probably step back a little bit. So when we get the done bit, we are no longer able to start the motor. So we can only start that motor 10 times. So what's going to happen is this normally closed is going to go what? It's going to go open. So it's not going to allow power to flow to this point anymore until what? We hit the reset button. We hit the reset button. It's going to drop that to 0. It's going to go ahead and close this normally closed contact again and allow us to start the motor again. And here we are looking at that very example. So here we are, seal-in circuit, hitting the start, hitting the stop, hitting the start, hitting the stop, back and forth till we hit a value of 10. All right, now we've hit 10. Now notice that you cannot hit the motor to get started again because what? That done bit is on. It's going to stay on until what? We hit the reset at that very moment when it's going to reset to 0, and as soon as we hit continue to start and stop the motor, we'll start counting again. So, also noting here, they have the accumulated value, the preset value, and all this information right here available in the data table. So here's an application where there's counting some cans. They've got show a proximity switch, something of this nature, and a reset push button. So you come in here, you have you're counting up, and as you continue counting, you got it's like they're storing it in 2 separate locations, and so when they close the box, you get C5:1, and then C5:2 is not used anywhere. It doesn't look like, maybe it's just the total count of packages possibly, and then some sort of internal here that says closed box. This is this B301, it's going to stay here. So this is going to count the number of packages. So every time we close a box, it's going to count that package. So we guess I can get up to 300 packages here. So every time that proc switch goes on, we count up the packages here. So and every time this thing counts to 10, it increments this value by 1. If you hit reset, it clears them all out. Pretty sweet. Very good. So here we are looking at the 5000 logics. Instead of a C5, we have what? We just call it package counter. We have the same registers. We have our preset accumulated value, and this particular time they call it package count. Under package count, we have .pre, .acc, which are both the 32-bit words. And then we have the individual bits of the control word, the counter up, counter down, done bit, overload, and unrun. A one-shot or transitional contact allows the user to automatically clear or reset a counter. Again, this is something we talked about a little bit earlier, I think in one of the earlier units, where we talked about one-shots and whatnot, where when you think of a one-shot, it's a transition that only is on for one scan of the PLC and then goes off. So that's quite often used to reset that of a counter. So here's, they're showing us some symbols and whatnot of how a one-shot would be displayed in a hardware configuration versus a software version, like a ladder program type thing. But basically it's just stating that's on for one scan. And they got an on to off or off to on state. So as you can see, it's only on for one scan in both cases. This is what we'll see in the 5000 and the 500. They have the OSR, the one-shot rising is what they call it here. They have a one-shot falling, OSF. But one-shot rising is the most typically used, and what it allows us to do again is monitor some signal, and it only triggers the reset for one scan. So and as you can see here, they've added the 1-3, which is a proc switch, in front of a one-shot to make sure that it's only counting one scan. And here's an example of how that's going to work for us. Noticing how that one-shot is only coming on for one quick scan. Application like this, do you have to use yet one-shot? No. Why? Because this proximity switch isn't being triggered more than once. It would work just fine without the one shot. But in this particular case, what they had to do is count to 50. When it reached the value of 50, it went ahead and reset the counter. So automatically, as soon as it hit 50, and then they also have a manual reset push button, which also allows it to reset. So. So here we're looking at instruction used to freeze rapidly display LED. One of the things you're going to run into is you're going to see applications where they're displaying values. Most of the time in today's environment, everything's done with Ethernet, so that value is going to change as fast as it needs to. You're not typically trying to hold information any longer than you absolutely have to, because you want the latest and greatest information, especially if you're having to create data for an application, and you want to make sure you have the latest and greatest information. So this would probably not be such a typical solution, but so they're converting some information from to BCD with a TOD command, and so they're allowing it to put some numeric value that's going to represent this number. So every time that that number gets triggered, the value in the simulator here will match the value of the counter of the timer at that time. Okay, so here we're looking at another application where they're doing some timers to, looks like a flasher circuit to me here, 4, 5, 4, 6. Remember, this is normally closed and normally open. That gives me right away, that lets me know it's a flasher circuit. So that flasher circuit is going to come over here, trigger this, and it's going to cause this counter to continue to count, constantly count. Every time we hit the selector switch, it's going to reset. So as you can see here, they just used some light and a counter, and just they set the count preset to 1. So what's very first flash it gets, it sets the done bit. The done bit comes down here, turns on the light. The light then is on until you hit the float switch, or the float switch. Or excuse me, the on-off switch here. The down counter. Okay, so now basically we're doing the same thing counting up when we're just going to count down. The one thing that we have to be aware of on the down counter, though, is that the down counter does not reset to a new preset value. Okay, you hit the reset on a down counter, it resets the accumulated value not back to the value of the preset. It resets it to 0. What does that mean for us? That means that when we're counting down, say we're counting down from 10, we're down to we get down to say 5, and someone goes and triggers a reset for that counter. You would say, intuitively, you probably are thinking, oh, that should set back to a 10. So when it starts counting down again, it starts counting down from 10. No, when you hit that reset, what it does is it puts a 0 in there. So the next value you trigger into that counter, that countdown counter, is going to be a -1. So keep that in mind. There's a question or so on the test regarding that as well. So here we are, we're looking at a count up and a count down. So we've got a counter up series, and we got a counter down series. As you can see here, when the address is the same for both of these, it counts up and then it counts back down again. So here's an application. When I say make sure you understand this, is C5:1, C5:, they got the exact same address. So you're taking that same value, this address, and you're incrementing it, so you're counting up, and you're using that same value and counting down. So if you trigger this, say 10 times, it'd have a value of 10 here, and you trigger this 10 times, it would be back to 0 again. So just keep in mind what's going on there. So here you're going to see the counter up getting triggered. As you can see, the numbers are changing in both. Now he hits this and it counts down. Pretty straightforward. Just that simple. Okay, the countdown works exactly the same as the count up. It has the same preset accumulated words. Both those are going to be 16-bit words. And then it's got individual bits representing all these, the counter up, counter down, done, overload, unload, UA. Countdown instruction. So here we're looking at an input to count down and the done bit when it reaches that value. See, now notice that that preset value was set to 2. As soon as it reached 2, that done bit turned on. Now that we're below 2, or when we were above 2 at 3, it was on. But when we went below 2, it was off. So you got to be equal to or greater than the preset value to have the done bit on. Here's the up-down counter program. Again, showing some of the details of counting up and counting down. So he's going to count to 5. Back down to 3. Done bit is on. He hit the reset. We brings them both back to 0, not to 10, back to 0. Keep that in mind. So a counter can be used something like this, count up, count down. So you're watching the parts go in, making sure you have the equal number of parts going out. That's not a bad practice there. So in feed, out feed, set to 0. So here we are looking at parts going in and parts going out. One thing in industry you have to be aware of, if you did hit the reset button and there was product in the machine, when you hit that reset button at that very moment, all that product would be what? Unaccounted for. So make sure you're aware when you're doing things like this that you're able to modify or adjust counts where you can come right into here and enter you could count the number of product in the machine and actually enter a value here to correct that after a reset was pressed. So it's not end of world problem, it's just issues. Cascading counters, again, when you get to 32-bit words, cascading isn't near as critical. When you're at 32,767 with a 16-bit word, it can be a problem. I've been there myself. I've had to set up cascading counters. The idea behind it, though, is that you're taking one counter, you count every time this first counter reached, say, 32,000, the next counter would trigger 1, and that was kind of the idea behind it, was to get you so you would have you could have multiple counters and count way beyond 32,767. So here, this one, it's going to count to 10, and then the next one's going to start to count to 10. When they both reach done, at that very moment, the light is going to turn on. So, give you an idea. So if you put, say, 32,767 here and 32,767 here, you could have what, twice as many counts before the light turned on. Think of it that way. And so here we are looking for really large counts. And so imagine 4, 5. Every time that counts to 5, that goes to 1. It's 5, and that increments by 1. at that very moment, it is when they both go in and then they hit the done bit. Complete. 24-hour clock. So here again, you can do minutes, hours. This is something that actually I've done a little bit with. I've done minutes, or seconds, minutes, and hours with counters and applications where I had to monitor or do machine uptime kind of thing. And these worked really well for that application like this. You can see it counting. We turn the timer. When it reaches 600, it's going to give this done bit, hit trigger this guy. This guy's going to trigger here. And that'll be that. I'm going to just zip this past here and see if I can make this go a little faster. There we go. So, monitoring of okay, so here we are again with the same thing. So here we are looking at a simulation time of an event program. So again, they're using some deal with a timer and some counters to add this all together and come up with solutions. I'm going to kind of zip through this pretty fast. You don't have to watch this timer count to 600 and all that business. So here we are, 599, counts to 1. As you can see, it triggers the done bit so fast you didn't even see it, and triggers the accumulated value of 1 here. So that's pretty much it for chapter 8. Counters. We're going to next break into chapter 15, part 4, programming counters in the control logics format. Okay, see you in a little bit.